Hi, for today's lesson, we'll be learning more about limits, limit laws, and how to use them to evaluate limits in calculus. Suppose C is a constant and the limits limit as x approaches a of f of x and the limit as x approaches a of g of x exist. Then the limit as x approaches a of the sum of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. This is also known as the sum law. For our second law, we have the limit as x approaches a of the difference of f and g. This can be rewritten as the limit as x approaches a of f of x minus the limit as x approaches a of g of x. This is the difference law. For our third law, we have the limit as x approaches a of some constant times the function of x. This constant can be pulled out in the limit evaluated here. This is known as the constant multiple law. For our fourth law, we have the limit as x approaches a of the product of the two functions f and g. These limits can be evaluated separately before multiplying. This is known as the product law. For our fifth law, we have the limit as x approaches a of f of x over g of x equal to the limit as x approaches a over f of x divided by the limit as x approaches a over g of x. This works as long as the limit as x approaches a of g of x is not equal to 0, the quotient law. If it were equal to 0, this would be division by 0, which would not work. For our sixth law, we have the limit as x approaches a of some function of x raised to the nth power. Now with this law, we can bring the limit inside, so we can evaluate the function's limit before raising it to some nth power, where n is a positive integer. This is known as the power law. For our seventh law, we have the limit as x approaches a of c equal to c. This is true because there's a function of x right here. For number 8, we have the limit as x approaches a of x equal to a. Because x is approaching a, x will equal a. For our ninth law, we have the limit as x approaches a of x to the n is equal to a to the n. For our 10th law, we have the limit as x approaches a of the nth root of x is equal to the nth root of a, where n is a positive integer. And finally, for our 11th law, we have the limit as x approaches a of the nth root of f of x equal to the nth root of the limit as x approaches a of f of x, where n is a positive integer. This is also known as the root law. You will continue to get more comfortable with all of these different rules and laws used to evaluate limits with more practice. So for our examples, each of these numbers correspond to the law. And also, there are two functions used. So this is the graph of f of x, where f of x is equal to 1 minus x squared. And this is the graph of g of x, where g of x is equal to 1 over x minus 2. So for our first example, we are taking the sum of two functions. So the limit as x approaches 1 of f of x. So we go over to f of x, we can plug in 1. Now, often when graphs are given a book, you can just look at the plot to find the y value if an equation is not given. So the limit as x approaches 1 of f of x will equal 0 because 1 minus 1 squared is equal to 0. And the limit as x approaches 1 of g of x will equal negative 1. So from all these limit laws, it may appear that you just simply plug in the x value where you see x. For our second law, we have the difference of the two functions. This time it's the limit as x approaches 3. So we plug 3 in to our functions and evaluate. We find that this is negative 9. For our third example, we have a c equal to 5. Here I specified a constant being multiplied, and I chose to use the limit as x approaches 2. As x approaches 2, this term right here approaches negative 3. And so we get the limit as x approaches 2 of c of f of x is equal to negative 15. For our fourth law, we get something very interesting. The limit as x approaches 2 of f of x times g of x. For our first function, we get that it's continuous. There are no breaks, no gaps, no asymptotes. For our second graph, however, we get an asymptote at x equals 2. This is because at x equals 2, this term goes to 0, and we can't have division by 0. Because g of x is undefined, this entire limit does not exist. For our fifth example, we have the limit as x approaches 1 of f of x over g of x. So we evaluate each function at that point, and we get that it is equal to 0. For our sixth example, I chose n equals 2 for this example, and we get the limit as x approaches 3 of f of x. So we go to f of x and plug in 3. We get that this is equal to 64 because when we plug in 3 here, then square this overall term, we get 64. Now please note for number 7 through 10, they're in red because they do not depend on either function f of x or g of x. So for number 7, we have, for an example, c equals 2. The limit as x approaches 10. Well, there is no x in here, so therefore it is equal to 2, because all we have right here is c. For number 8, we have the limit as x approaches 25 of x. Well, it has to equal to 25. Number 9, we have the limit as x approaches 2 of x to the n is equal to 2 to the n. And for number 10, we have n equal 3 in this example. And the limit as x approaches 5 of the nth root of x is equal to the cubed root of 5. And for number 11, in this example, we have n equal 5. And the limit as x approaches 0 of the nth root of f of x is equal to the fifth root of 1, which is equal to 1. So from these examples, we can see that for the limits, we can just plug in values for x and evaluate. Depending on whether you're given the graph or the function is how you will evaluate it. So limits are very important in understanding graph behavior. So I hope this helped you very much in your calculus course, and thank you very much for watching.